Hello, everybody. I am Edgar Bernal, a senior scientist at the Rochester Data Science Consortium at the University of Rochester. I'll be presenting the results of my work on training deep generative models with highly incomplete data. As a use case, the work deals with the task of data imputation, which consists in filling in missing values from partially observed data. Existing approaches model the complex statistical relationships between the observed data entries and use the resulting models to fill in the missing values. Our approach is no exception. We leverage normalizing flow models for reasons that will become apparent later on. I will first provide a quick overview of the evolution of the evaluation frameworks of imputation algorithms. Early data imputation work trained the imputation algorithm on fully observed data. Testing was done on partially observed test data. This approach is unrealistic as fully observed data may not be available for training in the first place. More recent work on imputation incorporated a more realistic benchmarking scenario in which the training data itself has missing values. This required enabling learning from incomplete data, which is a significant step forward. However, the testing happened on the same data used for training, meaning that the test data had already been partially observed by the algorithm. In contrast, we train on partially observed training data and test on a previously unseen set of partially observed test data, which we believe is a more appropriate approach for achieving fair and transparent performance verification. Next, I'll discuss the main limitations of existing imputation models, which this work aims to address. The plot illustrates one aspect of the imputation performance of three competing state-of-the-art imputation models as the rate of the unobserved data increases from 10 to 90% in steps of 10%. It is apparent that existing imputation frameworks work reasonably well when the rate of missingness in the data is small. However, as the rate of missingness in the data increases, performance decreases very quickly. In this work, we focus on the task of imputation for scenarios of high data paucity. When measuring the performance of imputation algorithms, there are three aspects of the quality of the resulting imputations to consider. The first one is how accurate the imputations are at the pixel level. The second one is how similar the population statistics of the imputed data versus those of the fully observed validation data or test data. And lastly, how well is the semantic content of the original image or data preserved in the imputed piece of data. Existing methods inevitably incur a performance trade-off between these three aspects. No single existing method is good at all three metrics. We aim to address these limitations. I will next provide a brief review of the features of normalizing flow models that this work leverages. Normalizing flow models are a family of generative models which are tractable and explicitly learn the data distribution. Specifically, we exploit the exact log likelihood evaluation, latent variable inference, and data sample reconstruction afforded by normalizing flow models. Latent variable inference refers to being able to compute the embedding representation of a given sample. Log likelihood evaluation refers to being able to compute the log likelihood of a given sample once a model has been exposed to a training set. Intuitively, the log likelihood of a sample indicates how likely is it for that sample to occur given the learned population statistics of the training set. Sample reconstruction refers to being able to uniquely reconstruct a sample given its embedding representations. This model involves This process involves computing a mapping from the embedding space to the data space, which is possible due to the fact that normalizing flow models are invertible. Next, I'll illustrate how to use a normalizing flow model to perform data imputation. Assume that a pre-trained normalizing flow model has been trained on a set of fully observed data. This is just a top example. Remember that in our testing scenario, we don't have fully observed data available for training. Now, assume we want to impute the missing values in a partially observed sample. Here, red pixels indicate image locations with missing values. In this example, 80% of the pixel values are missing. An intuitive way to perform imputation with a normalizing flow model would be to first fill in the missing values with some naive mechanism for imputation. For example, let's assume we impute missing values with a constant gray value of 128. In this step, you could use any shallow imputation method of your choosing, including nearest neighbors or any sort of interpolation. Once we have an naively interpolated image, we can pass it through our pre-trained normalizing flow model and perform latent variable inference and likelihood estimation on the resulting image. We proceed to sample the embedding space by moving in a direction that increases the likelihood of the image given the known data distribution and conditioned on the known pixel values that remain fixed. Once the new embedding location is determined, we can optionally reconstruct the sample to visualize where we are in the space and in the imputation process. We can continue moving in steps that result in increasing likelihood and stop iterating once a convergence criterion has been met. The goal of this process is to maximize the likelihood of the resulting reconstructed image given the known data distribution and conditioned on the known pixel values. Unfortunately, in imputation tasks of interest, the training data itself is incomplete. In consequence, construction of a normalizing flow model is not feasible. This is obviously because training a normalizing flow model requires complete, fully observed data. And as we saw in the previous slide, we rely on a fully trained model to perform imputation. On the other hand, getting better data involves having a fully trained normalizing flow model. We refer to this situation as a causality dilemma. We address the causality dilemma by alternately updating the model with the imputed data and improving the quality of the imputed data with the updated model. So we take our initial set of partially observed data, we naively impute the data. With this naively set of imputed data, we train an initial normalizing flow model. As we update the model, then we can recursively update the imputed data, improving the quality of the imputations. As we improve the quality of the imputations, we can then improve the quality of the model. We continue this process iteratively until convergence is reached. Remember, this is a purely data-driven approach, so the quality of the resulting normalizing flow model may be lacking, particularly in high data missingness scenarios. To illustrate this issue, recall that a normalizing flow model is trained by finding the parameters of the model data that maximize the log likelihood of the observed data. The question is, how well does the available training data, which has been naively imputed at least initially, represent the real or the statistical properties of the real underlying data? In order to address this limitation, we propose to enforce a shallow prior in the process of learning the normalizing flow model. In other words, we maximize a combination of log likelihood terms, one measuring the log likelihood of the observed data, and one containing the prior knowledge we have on the data. In this work, we enforce the hyper-Laplacian prior on the gradient map of the images and denote our framework as PR flow for prior regularized normalizing flow. Putting everything together, PR flow imputations are achieved by encoding the initial imputed sample using normalizing flow model G, optimizing its conditional likelihood using neural network H, and reconstructing the most likely sample as per population statistics and the enforced prior using the inverse of G. Note that in order to enable end-to-end learning of the imputation framework, we have replaced the iterative likelihood optimization in the embedding space with a fully connected feed-forward network. This has the additional advantage of performing optimization in a single pass at inference, as opposed to doing it iteratively as initially illustrated. We first illustrate the qualitative performance of the proposed method in an interactive fashion. The 4 partially visible images in this slide correspond to images of 4 numbers, where 90% of the pixels are missing. Can you guess what the numbers are? Feel free to pause the video if you'd like to examine the images more closely. We next reveal the ground truth, the images recovered by the competing methods, and the resulting error maps. Can be seen that PR flow produces the more realistic reconstructions, that is, images that are more number-like, and that it tends to recover the original semantic information encoded in the partially observed image. Also, the error maps show that PR flow is the most accurate at pixel level reconstruction. None of the methods reconstructed the last 2 examples correctly. However, the images reconstructed by PR flow are the more number-like looking. I would like to note that these are pretty extreme, difficult examples on which all methods fail to recover the original number. This is a similar exercise, except that it involves images of faces for which 60% of the pixels are missing. Can you guess the sex of the person in the image? How about their hair color? Is the person wearing accessories like a hat, glasses? Once again, results qualitatively show that PR flow produces the most realistic looking faces, as well as the ones most similar to the ground truth. Hair and skin textures, as well as facial features, are reconstructed accurately. Recall that none of these algorithms have ever been exposed to a single fully visible image of a face or a number. And so they have to infer what faces and numbers look like from piecing together the multiple available fragments from the different partially observed images. These figures show that PR flow is also quantitatively better than competing methods across all 3 metrics of interest, as well as all rates of data missingness. The plot on the left illustrates the average mean squared error, root mean squared error between reconstructions and ground truth. The graphic in the middle illustrates the Frechet inception distance between the original and the imputed data populations. And the figures, the curves on the right, illustrate classification accuracy of a classifier trained with fully visible data, as it runs inference on the imputed data by the 4 different methods. To close, we know that there is a trend in the community to build models that are able to ingest larger and larger amounts of data. As we showed, the over-reliance of machine and deep learning frameworks on data can lead to poor performance when data is partially observed. This is especially true in high data missingness scenarios. There are advantages to combining data and model-driven frameworks to overcome this limitation. We demonstrated the effectiveness of one such algorithm in the context of image imputation. Thank you for your time. This is my email address in case you would like to reach out with questions, comments, or if you would like to collaborate